your own point of view, it's better to use the avatar point of view, which means that you'll have on video exactly what you're seeing on the screen, besides public text chat and this kind of thing. If you want to record video, perhaps it would be advisable if you switch the name of the avatar off, and you find that in the Preferences menu under Tools. Anyway, just don't worry of making it especially nice. If you can record, just record. Okay, what I'd like to do now is, well, to invite people to sit down, because you have a much better view of the screen and the presenter. And also, perhaps, if someone wants to say some words to introduce themselves, we would very much like to meet the newcomers that we have. Everyone is very shy, I'm afraid. What happens here? A few practical things.
I'm sorry. Hi,
You're
this
not.
is Natasha.
Well, you know, Natasha, you're never shy. Randall, how to start? I suppose you mean the recording. You go into the Tools menu. I'm sorry, in the Actions menu, and you push Record Session. When you push Record Session, I'm doing that now, you choose the viewpoint. What I normally choose is Avatar Your View, and you choose the quality. I normally choose the highest quality. If you have bandwidth problems, you can choose the lowest quality. Okay, someone wants to see Natasha. Let's see if she's on our webcam. Yes, she is, but you know, unfortunately, I can only see the very top of her head. Here is Natasha on the left screen. Natasha, perhaps, you know, of course, you cannot be shy of your looks, because you are a very attractive woman, so perhaps you want us to see you better. We are seeing the very top of your head right now. We can really appreciate your haircut, but perhaps we want to see your smile. Ah, well, now I'm not seeing even the haircut of Natasha, but only the artwork she has in the background. Here she is. Here is to Natasha. Thank you very much for coming. Okay, and who else we have here? Right. We only have 3 screens. I have replaced me with someone else. This is Jameson, is it?
Yes, exactly. Jameson Dundon.
Right. Does anyone else wish to introduce themselves? Don't worry, I'm not recording now. Let's see who else we have here, because I see there is someone else. Well, Randall we know already. I think, well, I'm sure everyone knows Randall. In case someone does not, here he is. And Randall, say hello. And unfortunately, I invited many people over the last few days, so I don't really remember who MJH29 is.
Giulio, can you hear me?
Yes? Yes, sure.
Yes. I was just wondering if we could get maybe 2 words from most of the people who are here about what they do or what their interests are. I just kind of very curious to know more than the name.
Yeah, you know, people unfortunately are very shy, and especially in presence of 2 nice girls like today, they may be even shyer than usual. In fact, I was asking MJH29. Unfortunately, I don't remember who you are, because I invited many people over the last couple of days.
Sure. Hi. Can you hear me?
Yes, sure we can. And we can also see you now.
Okay.
Yes. So hi, I'm Max. I do neuroprosthetics work at Duke.
Ah, great, Max. Nice to
Nice to
meet you. We hear you very well. Perhaps the volume is a little bit low, so you may want to go to the tools menu in the sound sub menu and push the volume of the microphone a bit higher. Does anyone else want to introduce themselves?
I will. My name is Natasha Vita-Moore, and oops, that's a reminder to be in Teleplace. I'm working on my PhD dissertation on human enhancement and computation towards life prolongation and simulation at the University of Plymouth in England, and my own work engages human enhancement and life extension. I'm a transhumanist, and I don't know what else to say besides that.
Good, but I think everyone here knows very well who Natasha is. Let's see who else is here. I see there is someone in the lobby who is Michael Andreg, who I believe is Randall's boss, so we may want to wait for him. If it's the first time he uses Teleplace, he may need a couple of minutes to learn how to do that. Anurag is here. Someone who works for a high-tech computer security company, I believe. That's you, Anurag. I invited very many people over the last couple of days, so I'm afraid I don't really remember who is who. Does anyone else want to introduce themselves?
Can I say something, Giulio?
Oh, sure.
I just wanted to say thank you for my friend Georgina, who's here, and she worked in the same group where I did my PhD, so it's really good to see people here from that group.
Hi, Suze. I thought I'd stop by.
Thanks for coming.
Right.
No problem, I had it in the diary.
We are 23 people now. I would say let's wait for 5 more minutes for others to come. And then we can start. In the meantime, I will set up recording. I think everyone here has already learned how to use the system, at least to be able to attend a presentation. I have met many of you over the last couple of days. See that Michael is here. Michael, did you already learn how to use the system? Are you comfortable enough? The position of the microphone, the webcam, the text chat?
Let's see. So I haven't fully tested everything, but if you can hear me now, I'm going to be trying to put in my other microphone headset.
Well, we can hear you. We can hear you very well. The volume is fine. You see, if you want to go on webcam, you just push the icon next to the microphone. And if you want to use the text chat, you find it in the tools menu. And the text chat in the tools menu is the public text chat. Other thing that you may wish to know? No, nothing. I think you have already learned how to use this system. What we normally do when the speaker is giving her presentation is always a good thing to keep all microphones switched off and also all webcams switched off to save bandwidth. Who is this? This is Michael. I'm going to put him here. So when Suzanne talks, we just let her talk. We switch our webcam off. We switch our microphone off. And when the times come to ask questions, either you just switch the microphone on, or you say something in the text chat and ask for the floor. And at that point, you can also place your webcam on a screen. To place the webcam on a screen, you see that in the Tools menu, there is a sub-menu called Video Feeds. If you activate that one, you see a floating windows with all webcams. At this moment, we are 1, 2, 3, 4, 5, 6. To place yourself on a screen to be sure that everyone else can see you, you just drag the window with your webcam feed onto a screen. For example, now I'm going to put myself in place of Suzanne. And you see me on the same screen where you were seeing her. But you know, since now we can see Michael, but I believe that Suzanne is better than both. So I'm going to put Suzanne back. Okay. Now, in order to save bandwidth, especially in view of the fact that many other people will come, can I ask everyone to switch their webcam off? Okay. Let's put a nice image here. It's not that one. Okay. No, that's not the one I wanted. The one I wanted is this. Oh my god. I don't find the image that I wanted to put. It's something nice. This one. Right. Does everyone have the webcam switched off? Let's have a look. Natasha, you still have your webcam on. Perhaps you want to put it off now to save bandwidth. Right, let's put some image back. And we have only Suzanne. I will also like to ask everyone to switch the microphone off. Okay, now let me go to the other PC to start my recording. I have started recording from the other screen. Now I'm going to start also recording on this one. Just one little moment. Okay, so thank you very much for coming. We have already done the introduction of the last 15 minutes. So I'd like to give the floor to Suzanne for her lecture of quantum computing, which is going to be one of the most interesting lectures so far. Over to you, Suzanne. You have the floor. Also,
thank you, Giulio, and I hope it will be interesting. So I just want to check first that everyone can hear me.
The newcomers that we have.
Excellent. And my microphone volume is okay.
Everyone is very shy, I'm afraid. What happens here? A few practical things.
I'm sorry.
Why do I hear my voice?
Well,
you know, Natasha, you're, I think you're never shy. Randall, how to start? I suppose you mean the recording. You go into the tools menu, in the actions menu, and you push record session. When you push record session, I'm doing that now, you choose the viewpoint. Here it is. Here it is. What I normally choose is avatar your view, and you choose the quality. I normally choose the highest quality. If you have bandwidth problems, you can choose the lowest quality. Okay, I have switched the other recording. Let's start again. Suzanne, you have the floor.
Okay, thanks, Julia. Okay, so let me just sort this thing out. Just get the slides up. Okay, so today I'm going to talk about quantum computing, and hopefully this will be a nice introduction at a variety of levels, because I don't know who in the audience here knows what about quantum computing, so I've tried to keep everything as basic as possible, but I will be going into a little bit of detail for some of the slides, so if people want to ask me questions about that a bit later on, then I can do that. Fine, so I'm just starting the PDF viewer now. Okay, so can everyone see the slides on the main screen?
Yes.
Okay, great, thanks.
This is a test for Teleplace voice
Okay.
chat. This is a test for Teleplace voice chat.
Okay,
so let me just get this in full screen
I'm
mode.
going to start off with what I've entitled Fundamentals. All of today is interact.
Yeah, sorry about this.
It
It seems things are a little slow today.
Presentation. The idea is that we're going to get something new out of this, understand more about the questions.
Okay, so I have the slides now. Okay, so can everyone see those now on the main screen? I've got the PDF going. Great. Okay, great. So this talk is going to be basically there's been a lot the past few years, and the aim of this talk is really to try and separate what we can actually expect from quantum computers with some of the more outlandish claims that have been made about them. And so hopefully it will be an interesting talk about what quantum computers can do, but also it will be a little bit realistic and grounded about what we can expect them to realistically achieve within the next decade or so. Okay, so I'll just try to advance this slide. Okay, so the hope of quantum computing is basically as follows. So everything in the universe we think is governed by a set of laws of physics and mathematics, which operate at a very low level. So we expect computing to actually be constrained by these laws. There's no reason why it shouldn't be. However, most of the computers that we use nowadays actually work using the principles of classical physics. So you could build computers like this even if we knew nothing about quantum mechanics. So the basic idea of quantum computing is that we have laws of physics which are quantum mechanical in nature, which cannot really be simulated using classical physics. So the only way that we can simulate quantum mechanical systems is to use quantum computers. So really there are some things that quantum computers are supposed to be able to do that classical computers really cannot do in any reasonable time frame. So that's the reason why we want to really build quantum computers, because the way our universe works is quantum mechanical. So we want to have computers that actually mirror that and actually are able to incorporate that into the way that they work. However, there is also a lot of hype about quantum computers. So I put some statements up here, and most of these are wrong to varying degrees. So one of the ones that a lot of people say is that quantum computers can break cryptographic codes, and this will basically throw everything into turmoil. Life as we know it will be turned upside down if RSA is broken and these things. Another one is that quantum computers are exponentially faster than classical computers. Another one I often hear is that quantum computers can do all calculations simultaneously by tapping the power of the multiverse, which is something that I would call hype rather than a grounded statement. And the other one is, so this one is a bit more technical, but it's also cited a lot, which is that quantum computers can solve NP-complete problems in polynomial time. So, excuse me. If you don't know what that means, then don't worry about it, but it's something that causes a lot of confusion in the field of quantum computing. But these things are all wrong to varying degrees. So we'll see if we can go through the talk and explain what quantum computers can do and why all these statements are wrong. Okay, so first of all, we have to start by defining what we mean by quantum computer. So we can't start to build something until we actually have a definition of the thing we want to build. So the definition I use for quantum computer is a machine that uses the quantum effects of superposition and entanglement as part of its intrinsic computational operation. So this answers the question of, so say your Pentium 4 chip or whatever the latest processor is consists of matter. It consists of atoms and electrons, which obey the laws of quantum mechanics. So why isn't your desktop PC a quantum computer? And the reason is that it's not actually using those quantum effects as part of what it's doing. If those quantum effects weren't there, then we would still in theory be able to use that processor to do the same task. So a quantum computer actually has to use some property of quantum mechanics which is not accessible using a classical processor or classical physics. So on the next slide, I have my checklist of quantum effects. So these are the things that we want from a quantum computer. We want some kind of superposition of states and some kind of entanglement of states. And I'll explain what these are in the next slide. There's a third one, which is decoherence, and this is unfortunately an unwanted effect that we get as a byproduct of trying to build large quantum systems. So these are the effects that you need to harness to be able to use a quantum computer to do something more powerful than a regular computer. Okay, so what are superposition and entanglement? So the idea in regular computing is that you have a classical bit which is either in a state 0 or a state 1. And a quantum computer can actually have what's called a linear combination of both these states in varying amounts. So the little picture on the right at the top is what I'm using to denote my qubit, which is a quantum bit. And you'll see why I actually choose this little diagram in a while. But for the moment, I'm just putting it there so I can have a representation of a qubit. So you can see that the qubit can have a combination of the state 0 and the state 1 in varying amounts A and B. Okay, so that's the superposition. And then you have the entanglement property, which this is a little bit more unusual, we should say. So this is where you actually have 2 or more qubits, and the states that they're in, whether they're superposition states or not, it doesn't matter, but the states that they're in are somehow locked together. So if you have a qubit, you prepare 2 qubits in 2 states, and then you separate them by a very large physical distance, then one state will still depend on the other, even though the qubits might be on the other side of the universe. So this is a very unusual property. So so imagine you put two qubits in an entangled state whereby one of them was 0 and one of them was 1, but you didn't know which one was which. And then you separate them for a vast distance, and then you measure one, and the one on the other side of the universe automatically chooses which state to be in. So you might think, well, how does this happen? This seems very odd. It actually doesn't violate any laws, such as it doesn't violate, say, the speed of light, because you can't actually transfer the information. You can only transfer the quantum state. But this is the property that Einstein thought was very spooky when the quantum mechanics was originally being formulated. But in fact, it's something that occurs very regularly in quantum systems, and there have been lots of experiments to show that it's actually happening. Okay, so we have our checklist of our quantum effects. So why can't we just build a quantum computer using these? So what are the problems? Okay, so this is in one slide why it is really hard to build a quantum computer. So when you take your regular components, for example, your transistors, you only need to make one transistor that works really well. Then you can just duplicate it, say 100 times. You can get them all to talk to one another, and your computer will be 100 times more powerful, for example. With a quantum computer, things don't work quite that easily. So here at the bottom I have a picture again of my little qubits, and so the two qubits on the left are quite happy because they're being kept separate, and if you look at each qubit on its own, it's very happy. But when you try and put two of them together and use that joint object to do a computation, you actually run into a problem in that it doesn't scale. You can't just stick these things together like transistors and hope that they do the same thing. And unfortunately, it's kind of a double-edged sword, because the very fact that there is this entanglement and superposition gives you the power of the quantum computer, but it's also this thing that causes the qubits not to scale in the same way that transistors do when you try and put them together. They're actually locked together. So it's quite tricky to explain, but this is really the main problem. And the mechanism by which this problem arises is known as decoherence. So I think I've got a quick slide on decoherence. Okay, so decoherence is really the enemy of quantum computing, and it's what we're always trying to fight against all the time. Okay, so basically what decoherence is. So on the right I've got a picture of a bunch of qubits, and as you start to stick qubits together, they become more and more sensitive to what's going on around them. So it's really easy to isolate one qubit from the environment where there are lots of things that it can interact with. However, when you start putting lots of them together, they're much more likely to interact with the environment. And decoherence occurs anytime you have a qubit which is talking to the outside world. So all these methods of decoherence, such as stray electric fields around the place, magnetic fields, defects in the materials from which you're making qubits, and even temperature itself, can cause decoherence, which is the destruction of the quantum states, of the delicate quantum effects that you're trying to use in your computation. So this is the main reason why progress in quantum computing has been so slow, because it's trying to find ways around this problem of decoherence, trying to keep those quantum effects going for long amounts of time. And it's not as simple as people think. Okay, however, I believe that we should build quantum computers anyway, despite all this problem, because, like I said before, standard computers are not very good at modeling quantum systems. So even if quantum computers have absolutely no use in any kind of problem solving, which is very unlikely because it looks like there is a kind of speed advantage to running quantum computers in certain ways. So even if none of that works, then quantum computers are still the only way that we can feasibly simulate quantum systems. No one's come up with a good algorithm to run on a classical computer that can even calculate the levels of the energy levels in molecules, for example. It's very difficult to do these calculations that involve the quantum mechanics, the equations and theorems of quantum mechanics. If we had a quantum computer, those equations would be built into the very operation of the computer, so it would be able to do these quantum mechanical calculations very quickly. And I think this is really important for our understanding of the way the world works, because if our universe is operating quantum mechanically, then surely we want computers that also operate quantum mechanically to help us simulate and understand that real world. So here I put the picture of the atom, which is really the picture that people are taught in high school, or maybe below, which is the way that the atom looks classically. However, we know that this is not the way the atom really works. So why are we still building computers that work on this using these classical pictures when we could be building computers that work according to how the real world works? Okay, so things are not quite so simple in quantum computing, and slide to explain why. Okay, so the idea of this is that not all quantum computers are born equal. So if someone says, let's just build a quantum computer, then they don't really know what they're talking about. You can't just build a quantum computer any more than you can build a generic vehicle. So if someone says, I'm going to build it, if someone says, I want you to build me a quantum computer, your first question should be, well, what do you want it for? So here is my analogy with cars and vehicles in general. If someone says, I want a vehicle, you'll say, well, what do you want it for? Do you want a sports car or do you want a tank? Okay, so this is the analogy with quantum computing, is that there are lots of different features that can be incorporated into a quantum computer, which will make it completely different depending on the task that you actually want it to do or to perform. And the way this is actually described is in terms of algorithms, models, and implementations. So this is really the really important point of this talk, and it's actually where most of the confusion about the power of quantum computing arises, even amongst the people that are working in the field. So, if nothing else, remember this slide. There are three features when you're designing and building quantum computers that are really important. And I'm going to try and explain them in terms of how you think about them for classical computers first, and then I'll explain why they also occur in quantum computing. So the first question is, what algorithm are you running on your computer? So this is, what problem do you really want to solve with this computer? The example I've put here is, how would I invert a matrix? But there are all sorts of different algorithms you could ask. What's the best way to search a database? Or what's the best way to organize a sequence of tasks so that the resources are allocated correctly? So this is really important, and how you build your computer actually depends on what algorithm you want to run. It's very hard to build a general purpose quantum computer. So the second thing is the model with which you're basing your quantum computer on. So this is the hardware model. You can think of this as being like different computer architectures. So the standard architecture for processors, at least up until recently, has been kind of von Neumann architecture, where the computation and the memory kind of separate, and you have basically a single core processor that's doing most of the work. But then you can also have distributed or parallel computing, and you can even have architectures like neural networks. And all these different architectures are good at running particular algorithms, but none of them are good at running all algorithms efficiently. So, for example, it might be like taking the hardware architecture of your graphics card and asking, well, why can't this graphics card route network traffic very well? And so you can now see the problem. It's like, well, you're asking it to do the wrong thing. So this is very important with quantum computers, because the way you build it is very tightly connected to what you actually want the thing to be good at doing. Okay, so the third point is the implementation, and this is actually how you build the computer itself. So this is not something people really think about very much with classical computing, because most of it's built using silicon technology. However, if you think about it, you can really build a computer using anything. So it doesn't have to be made of silicon. It could be made of water flowing through pipes, if you wanted to calculate how water flows through pipes. It could be beads on a string, like people used to count using abacus. It was a form of computing. And you could even use ants. So I don't know if anyone has read the Discworld series, but you'll know that there's a computer which operates at Unseen University, basically harnessing the power of ants to do very complex computations. So I thought that was a nice example of a computer running on a different kind of substrate. Okay. So now we have our three main features of quantum computers. I shall explain how this maps over from classical to quantum. So in quantum computing, you also have different algorithms. For example, Shor's algorithm, which a lot of people have heard of, which is useful for factoring large numbers. There's also Grover's algorithm, which is useful for searching databases, and there are a bunch of other algorithms. And then the models of quantum computing are similar to the hardware architectures. So we have the gate model, adiabatic model, measurement-based model, and topological quantum computing. So the first two are the most popular types of models that most people try and build their quantum computers to use. So the actual way that you build the hardware is usually a gate model type system or an adiabatic type system. The other two are still a little theoretical at the moment, and no one has yet found an implementation that could actually run those two models. But it doesn't mean they can't be done. It just means that a suitable substrate hasn't been found yet to run those. And coming on to substrates, the third point is the implementations. So this is the actual underlying physical thing that's doing the quantum computing. So there are basically lots of different ways to build quantum computers. So I've just put a list of a few here. I'm not going to go through them in detail now, because I have a couple of slides on the implementations a bit later on, because I think it's very important to explain different ways in which you can actually really get to work and build these things. So I'll come back to that. Okay, so just a little bit about the two main models that I mentioned before. So the gate model is, so just to remind you again, this is the actual architecture that you would use to build your quantum computer. The gate model is the most common, the most popular model for quantum computing. And the reason is because it's a very familiar approach, it's easy to understand. What happens in the gate model is that you have logic equivalents of classical gates, for example, AND gates or OR gates. So you've got your Boolean logic. And in the gate model, each of these gates is replaced by a quantum equivalent. So these little circuit diagrams I have at the bottom here show that so the boxes are each types of quantum gates. So it's not really important to know what types. You can ask me afterwards if you like. But the important thing is that these look very similar to regular circuit diagrams. Okay, they're gates connected by wires, and information flows through the circuit from left to right. So you can kind of track the quantum information as it goes along through the gates. You can see what happens to the information as it gets operated on by a gate, and you can follow it through. So this is a very intuitive way of thinking about computation. However, it's not the only way that you can do quantum computation. And I'll argue that this method is actually inferior because it's very prone to decoherence. So each of these tiny little gates is very open to a lot of the effects of the environment that I've been talking about, and the quantum information can be lost very easily when you use this kind of scheme. So I'm going to argue that adiabatic quantum computing might be a better way of doing this. And one of the reasons that I'm advocating this is obviously the company I work for is trying to use this hardware model to build a quantum computer. So I'm obviously very excited about this particular method of doing it. So the way that adiabatic quantum computing works, it's a completely different paradigm, so forget everything you know about logic gates now. This is more like what's known as a physics-based approach. So I don't know if people here are familiar with the traveling salesman type problem. So if you tried to solve a traveling salesman type problem using logic gates, it's very difficult. So this computational model is much better at solving these kind of problems. So very quickly, the traveling salesman problem, you have a bunch of cities and you have a salesman who wants to visit each of the cities, perhaps to sell quantum computers, perhaps not. And the idea is that he wants to get around all the cities in the shortest time or via the shortest route possible, so he's not wasting time. So you can see on the left there are different ways in which you can visit all the cities in turn. And unfortunately, as the number of cities increases, this problem becomes extremely hard to solve because the number of possible routes you could take explodes exponentially. So actually finding the best one is very tricky. However, it happens that to be that finding the best route is equivalent to finding a very low energy configuration of the system. So you can imagine if you had a very long route going between a city that was very far away from the start, you can see why you wouldn't do that, because you'd obviously go to a closer one first. So you can look at finding the shortest route as minimizing the energy of the system. And people solve these problems using a technique called simulated annealing, which is where you start off contemplating all the possible routes that you could take through the city, and you take all these into your computer program, and then somehow you kind of mix them all up. So you might do this using a genetic algorithm or some other technique. And what happens is you slowly lower the amount of disorder or the energy in the system, and eventually the kind of jiggling around between all the different possible routes should end up finding a low energy configuration. Again, this is a little bit tricky to explain in 5 minutes, but so I've drawn a diagram on the right which shows a kind of energy landscape. So you can imagine the red dot sitting in the relatively low energy state is a good configuration, but it's not the best configuration of the cities. But by jumbling them up around a bit, you've kind of got stuck in what's known as a local minimum. However, to find the global minimum, the best route, is actually a very difficult problem. And even thermal annealing gets stuck on this problem. So you can see in the bottom picture on the right, would it get stuck in a local minima, finding a reasonably good solution, or would it find the best solution possible? Thermal annealing probably wouldn't. However, adiabatic quantum computing can actually solve this similar problem, but by using quantum mechanics. So what I've shown here is a picture of lots of qubits. So each qubit consists of a spin, which can be up or down. So you start with your traveling salesman problem, and instead of contemplating all routes at the same time, you put all the qubits in a superposition state, which is kind of doing the same thing. You're saying they can all be either on or off. So each route would correspond to a qubit. And then what you find is that because you have these quantum effects in your system, this superposition and entanglement, is that when you lower the energy of the system, you actually don't get stuck in the local minima anymore. The quantum system is much more likely to find the ground state of this problem than classically. And as some of you noticed in the text chat, this actually occurs via quantum tunneling, which is a byproduct of superposition. and entanglement. So you can think of the system getting stuck in a local minimum, but then it's able to escape even if the system no longer has the energy to jiggle about the states, so it can escape from the local minimum. So this is an example of how a quantum process can be used to solve really hard problems that's completely different from this logic gate approach. So you can see now how the different hardware models really can be a little bit confusing, but they tie in very, very tightly to what kind of problem you're actually trying to solve here. This adiabatic approach uses a large number of qubits to encode all your variables at once, as opposed to using 1 or 2 qubits per logic gate. Okay, so enough about models. That's all really boring. So how would you actually build a quantum computer? What would you do? So let's see. As a rule of thumb, you can think that anything that's small or cold usually ends up exhibiting some kind of quantum mechanical effect. And we could say that more formally. So any system that has a well-defined quantum variable that has 2 states can be used to make a qubit. So it happens that in nature there are many systems that have these nicely defined 0 and 1 states and are also small enough to exhibit the quantum effects that we require. So there's just a little schematic diagram on the left, but what you can see is, for example, the spin on an electron can either be in an upwards pointing configuration or a downward pointing configuration. But because electrons are quantum mechanical objects, you can also get a superposition of the up state and the down state at the same time. So you take these electrons and you can use them as qubits. So you found a physical system where the quantum mechanical effects map onto your computational problem that you're trying to solve, because you want variables that have 2 states, like a bit, so 0 and 1. So you find this effect in atoms, electrons, photons, lots of other kind of small physical systems. Okay, so here are some of the implementations I was mentioning earlier. And so there are, for example, ion trap systems, which use ions, obviously. Then there are NMR-type quantum computing schemes, which actually use atoms in various places along a molecule. Nitrogen vacancy technology, which is almost a nanotechnology. I'm not going to talk about that in detail because no one's actually done it yet. But if people want to ask me about that later, then that's fine. And then there's also superconducting electronics, which uses the quantum variable on the electron to encode the information. So what I'm going to do is just go through each of these in turn and show you some pictures of how you'd actually make these things in real life. Sorry, the slides are being a bit slow. Okay, so here's the first one, which is ion trap quantum computing. And what you have here is you can actually take ions, which are atoms with electrons removed from them, so they're actually charged objects. Whoops, sorry. See, I knew I clicked twice. I was being impatient. Okay, just have to wait for Teleplace. Okay. Try once more. Yeah, it is. It's very slow. Like I click and I have to wait 10 seconds for the slide to change. So it's a little bit frustrating. But as long as I know I clicked, it's okay. So I'll start talking about, okay, ions. Here we go. So like I was saying, the ions are atoms with some of their electrons moved. So they're charged objects. And because they're charged, you can actually trap them in an electric field or a magnetic field. And so what actually happens is that people trap like little sets of ions in chain, or they line them up, and the ions can actually talk to each other. So the way they do this is they interact both electrically and via vibrational interactions. So you can imagine if you move one of the ions, then its neighbors will actually be able to feel that motion of one of the ions moving. So if you move all the ions in the correct way, then you can actually encode a computation into this. So it's a very kind of hand-wavy overview of how it actually works. But you can imagine these as being like tiny little kind of beads on a string, as I was saying before. And so if you move one of them, it has an effect on the others. So this has actually been realized in some integrated circuits. You can see that on the picture in the left. These tiny ions which actually float above the surface of the chip. This thing also works at room temperature, which is an advantage, and you control the ions by sending RF radiation to them through little electrodes on the chip. So unfortunately, in order to get the traps working, and you actually have to address them using laser pulses as well, you need very complicated set of apparatus, such as the one shown on the right there. So this is what real quantum computing in the lab looks like. I mean, it's not like drawing equations on a whiteboard, which is what most people think of when they think of quantum computing. It's actually really difficult. The equipment is very specialized. You need high vacuums, you need high power lasers, you need magnetic shielding systems and all kinds of interesting equipment. So it's certainly not a mature technology at the moment in as much as, you know, you can buy these things from PC World. they really are huge pieces of equipment. So they'd probably scale down over time, but at the moment they're pretty large. They take up entire rooms. Okay, so the next one I'm just going to mention is the NMR quantum computing, and the way that this works is you have an ensemble of molecules, say in a small vial of liquid, and each molecule has atoms located in particular places which have nuclear spins. And the nuclear spins are sensitive to NMR techniques. So what you can do is you can apply very large magnetic fields to the molecules, and you can actually look at the nuclear and the splitting of the atomic energy levels by the nuclear energy levels. And again, there you've got a system where there are atoms with energy levels, so you can use this for quantum computing. However, the problem with NMR quantum computing is that each molecule, so you have to pick a molecule that has the right qubits. So the molecule on the left here, I think, shows 7 qubits. But you can imagine trying to scale this is very difficult, because you have to find and the next molecule up has to have 8 qubits, and then the next molecule up has to have, I don't know, 20 qubits. And so it's like, well, eventually your molecules start to get really complicated, and it's actually not a very scalable approach to quantum computing. But on the upside, this actually has been shown to work. So IBM famously got this 7-qubit system to work, which was actually able to run an algorithm, in fact, to the number 15, which may not sound like much, but it's a proof of principle, which is very, very cool. Okay, so now we move on to my favorite implementation. So I'll have to go through this bit quickly now because I'm running out of time. So my favorite implementation is known as the superconducting flux qubit. And superconducting qubits are loops of metal, which when you cool them down, because superconducting superconductors are described by quantum mechanics, not by classical mechanics. They actually end up having energy levels just like atoms, even though they're large loops of metal, which is interesting. So what happens in a superconductor is when you cool this thing down, the current that flows around these loops and the magnetic field that threads through the loop as a result both become quantum mechanical. So if you choose the correct magnetic field to apply to your qubits, then you can actually get the currents that are flowing around the loop to end up being in a superposition of states. So you've got a large object which is acting just like an atom. So it's got an energy level with the current flowing one way and an energy level with the current flowing another way. Okay, so the reason, well, there are several reasons why I like superconducting qubits. And one of them is that they're actually made in a very similar way to CMOS devices. So if you look at the pictures on the left, you can see these are electron microscope pictures of superconducting qubits. And they actually look fairly similar to the way in which you'd pattern standard circuits. So they're between about 0.1 and 10 microns in size. And the other interesting thing about superconductors, which is a bit of an aside, but they do not dissipate any power in certain modes of operation. So you can imagine making huge circuits comprising of just superconducting electronics, which doesn't really generate any heat, which is quite impressive because one of the main problems with CMOS chips nowadays is actually getting the heat out of the chips. So this is a very promising technology for computation in general, not just for quantum computation. I noticed someone says it looks like a double exposure. That's because it is. So the way they make the junctions, the qubits, is by doing a double exposure of the material, which is pretty cool. Okay, so let's just move on. I'm still here just waiting for the slide to change again. I don't know why my network connection seems so bad today. It's usually pretty good. Okay, there we go. I've got it. So sorry, the question is one for detecting the qubit, one for running it. It's actually not that. The thing is, when you're making a qubit, you have to make what's called a Josephson junction. So the way that this works is you put down one layer of metal and then you put a slight oxide on top of it, and then you put down another layer of metal, and this actually makes what's called a Josephson junction, which is the part that does the quantum computing. But you need to get this sandwich structure, so that's the reason you put down two metal layers. So you see this double exposure technique. So back to the slides. The other reason that I like superconducting flux qubits so much is, as I mentioned, they're compatible with existing processor fabrication methods, which means that they're scalable. This is really important. So semiconductor foundries now, if you want to start a semiconductor foundry to make integrated circuits, it costs billions of dollars. Which is crazy. If you're trying to make a quantum computing technology, then that kind of money just doesn't exist. So actually having a process like superconducting electronics, which is already we can take the best practices and all the information that's been learned from making semiconductor chips and use that to make superconducting chips, then that's actually a very powerful method. So you see here on the right pictures of wafers. The first one is like a CMOS standard processor wafer. I think it's made by Motorola. And the bottom one is one of the D-Wave superconducting processor wafers. So the idea here is that they're supposed to look very similar to show you that you can use the same techniques as you use to make semiconductor devices to make superconducting ones. It's just that the materials are different. The other useful thing about superconducting qubits is that when you build your set of qubits, that's not all you need. You need a lot of circuitry that surrounds them to actually get the information into the qubits and get the information out again when it's done the quantum processing. And people seem to neglect this a bit. And when you only have 1 or 2 qubits, it's really easy to do. But if you had 1,000 or if you had 1,000,000 qubits, you'd need a lot of on-chip circuitry. It might be standard CMOS circuitry or something, just to get all that information in and out. And so the other reason I like superconducting qubits is because there's an entire logic family based around superconducting hardware which already exists, and people have been working with it for 30 years or so, maybe more. So this is really important because on the same chip as you have your qubits, you can also build lots of electronics to talk to your qubits from the same materials. So it's kind of really integrated onto the chip. However, there are disadvantages of superconductors, which are they do require some extreme environments to work. So you need to have a very low temperature, you need to have a very low magnetic field, and also superconducting qubits are quite prone to this decoherence effect that I was talking about before. So although you get all the advantages of the scalability and the materials technology and the electronics, the auxiliary circuitry, you have to overcome some really difficult problems. So one of the problems is that you have to cool the superconducting qubits down to approximately 20 millikelvin, which is 0.02 above absolute zero. So that's in degrees, which is quite cold. They also need very extreme shielding from magnetic fields. So if you remember before, I said that the superconducting qubits work by having a very small magnetic field applied to them. So it turns out that you have to get rid of all other fields so that you can talk to the qubit in exactly the way you want. Otherwise, it'll talk to the Earth's magnetic field, it'll talk to all the magnetic fields coming from electronic equipment, this kind of thing. So you need some very carefully shielded environment to put your qubits into. Julia asks, doesn't decoherence grow exponentially with the number of qubits? The answer to that is no one knows. Okay, it's an open question in research, which is why people are trying to build quantum computers using lots of different hardware models, because some people believe it won't be as bad in certain models as in other models. So really it's just a question we have to find out by building them. No one knows the answer to that question. Okay. We do know it's actually harder to get rid of decoherence as you scale the number of qubits, so you have to work pretty hard to get them to work. Just a quick myth in case anyone asks. So when I say these superconductors have to be cooled, people say, oh well, can't you, if we found room temperature superconductors, would that solve the problem? And the answer is no, because what you're doing is you're not just using the superconductivity, you actually have to cool them down to get the quantum effects to appear in the first place. So even if you had a room temperature superconductor, you'd still have to cool it down to millikelvin to actually see the quantum effects happening. So yeah, it's similar to Bose-Einstein condensation. That's actually the electrons are actually condensing in the superconductor. So, okay. Yeah, so no room temperature superconductivity quantum computers in the near future, I'm afraid. It's not going to happen. Okay, I apologize if my talk runs over. I'm having to wait 10 seconds between each slide. So sorry about that. Yeah, I learnt my lesson by clicking twice earlier, so I'm not going to click again now. Okay, so here is a picture of what I think is probably the most advanced quantum processor that's been built in the world. So as I went through earlier with the different schemes like the ion traps and the NMR, I was explaining that they use the gate model and they run particular algorithms. This one runs what's known as an adiabatic quantum optimization algorithm, which uses the adiabatic model. It's probably pretty obvious from the name. And this is implemented again with the superconducting qubits. So these are the processors that D-Wave make. And because they're running this optimization algorithm, which is the one that solves the traveling salesman problem, you can actually put lots of qubits together straight away to run the algorithm. And so it's different from the gate model where you have to start like tying them together in these logic gates. So most gate model quantum computers only have like maybe 1 to 5 qubits, maybe 1 to 10 at the moment, whereas these adiabatic ones you can start with a large number of qubits because it's running a different model. Okay, so the picture on the left shows 8 qubits. They're arranged horizontally and vertically as lines, and they cross over each other. And then the picture on the right shows that thing multiplied by 16 times. So that's 128 qubits in total. So they're all connected to their neighbors, and you're able to run this algorithm on this processor. Okay, so I'm just going to very quickly go through some of the applications that these kind of chips can be used for. How well do many chips work together? Well, we don't know yet, but it's something that's actually being investigated. I mean, getting one to work is really hard at the moment, so we're trying to scale them, basically. So the first kind of application is what I mentioned before, is these graph applications. So this is anywhere where you have a kind of a routing problem or an optimization problem. So by routing, I mean you can think of things like traffic, actual real vehicular traffic being routed, or you can think things like network routing of packets on networks. So it's like, what's the optimal way to route network traffic which will avoid bottlenecks and avoid congestion? And actually trying to find this out, say, based on the load on your network at a particular time, is actually a really hard problem. And it maps quite well onto this traveling salesman problem. You can also think of component layout and microprocessor design as a very difficult problem. So when you're trying to place components on a circuit board, it's actually really hard to decide which one goes where to minimize the amount of wiring that you need and how well the circuit will work. So actually solving some of these component placement problems and these routing problems is really good industrially applicable use for these quantum chips. Also in biology, there are a lot of applications. So at the moment, the amount of data involved in bioinformatics is just exploding. If you think about things like gene sequences, think about things like databases of metabolomic pathways, we have all this data, but what we don't have is very good tools to search it and to actually go through the data and pull out useful results from that. So one of the promising applications for these quantum chips is actually finding patterns in large amounts of data. So, for example, pattern matching in gene sequencing, or looking for particular molecular signatures in NMR spectroscopy or any other kind of spectroscopy you can think of. They also, protein folding is one application that also maps particularly well onto these chips. So at the moment, the problems that are being solved are still very small, but the idea is that the proof of concept is there, and as long as you can scale the chips up, you should be able to scale the problems up. So they should be able to tackle some very interesting industrial problems. Yes, okay. So another one is security applications. So this is the one that most people think of when they think of quantum computing. So there is cryptography and code breaking, or code securing, if you prefer to be a bit more optimistic about it, is actually a very good use of quantum computers. Then there's also, again, I mentioned about searching for patterns in large databases. You can think this is kind of the same problem as image recognition or biometrics, when you're actually looking for some specific pattern or feature in a large amount of data. So imagine your airport security with your video feeds coming in constantly, and you're looking for specific features of things that are maybe unusual occurring in the airport. So it would be really hard for humans to do this in real time. I mean, there's just so much information and people would miss things. And it's even hard for supercomputers to do this in real time because the amount of data that's coming in from these feeds is just really tricky. So if you can have a computer, say like a quantum computer, whereby the algorithm it's running is much better tuned towards these particular applications, like finding features in images, and it might be that these processors are just much better, even though they're smaller than supercomputers, at solving some of these tasks. So another example is database searching, as I mentioned. Scanning network traffic is another one. So you've got all this network traffic moving about in real time. Quantum algorithm might be very good at detecting particular anomalies in that network traffic or particular sequences that people might be looking for, say for national security or something like that. I'm not sure what the reverse phone book problem is, but you can ask me about that. I can ask you about that later. Okay, so finally we'll just move on to what I think is one of the most promising applications of quantum processors, is that they can actually be used for AI applications. So as I mentioned, pattern recognition and database searching and feature detection are all problems that these chips are very good at. So it's not a very big step to go from there to things like pattern recognition and machine learning in artificial intelligence. So in a way, you can think that these chips are actually doing tasks that humans are very good at, and they might be doing these tasks a bit better than the way we build computers classically. So I actually think that this type of technology is very brains and basically exploring new ways of building neural nets. In fact, I have a slide on neural nets, which should be here. So this is just to show you that all these bullet points I'm putting up is not just like pie in the sky. So here is an example of how you might use the quantum chip to do machine learning. So on the left, I've got the little array of qubits, and what you do is that you feed this. You can think of it like a neural network. So it's an array of coupled together elements, and what you do is you feed it training data, and the connections between the qubits start to be made as you give it more and more data. And then what you do in the end is you take this thing that's been trained, this network of connected qubits, and you feed it some new data which it's never seen before, and it's able to recognize features in that data that were similar to what it saw in the training data. So this is actually a way that people build like detectors for particular objects in images, like cats or cars, in fact. And actually this has been tested. So one of the D-Wave chips was used to train a car detector in a collaboration with Google, and it actually works really well. I think it beat the one that they were using before, so it actually detects cars better. So something that's actually been trained using a quantum computer is now outperforming the previous incarnation of these detectors. So they really are working. I mean, it's not just talk. These things are actually being built now, and there are many more possibilities with these neural networks as the chips get much bigger. So just a couple of my predictions for quantum computing. So when are we going to see quantum computers starting to do useful things and becoming commercially available? Well, I would argue that they already are kind of doing some small tasks. And I think within the next few years, we'll start to see some commercial applications of quantum computing. I mean, you can already buy photonic systems for, say, secure data transfer. So that's an example of a quantum system that's been built and is sold. Then there are these adiabatic chips I was mentioning that D-Wave are making, and I think these will be solving useful. They already are solving useful problems, and so it will be interesting to see how many more problems they'll solve as they scale up. I think the gate model quantum computing is probably much further away because, like I said, it has a much harder problem with overcoming decoherence. However, I still think it's a very good goal to pursue, because the gate model can run a lot of different algorithms that AQC can't run. So I think it's useful to make an entire spectrum of all kinds of different quantum computers to solve different algorithms. So we have all these special purpose chips to do certain tasks really, really well, instead of just trying to rely on general purpose computing. And in a way, you can even see this happening with classical computing. So people are now moving over to more distributed computing, more special purpose co-processors to do specific tasks. So I think that this will happen in quantum computing too. And in terms of the implementations, I think that obviously I think superconducting hardware is a very promising way of realizing this. But I also think that the results from the ion trap quantum computing have been very successful, and possibly even in the future, depending on how well the field of nanotechnology evolves over the next few years, I think that something like the nitrogen vacant quantum computing could also be a very good candidate, because that's also fairly scalable. It's just a big technological challenge at the moment to actually manufacture those kind of qubits. Yes, in response to Rob, I'll say a little bit about that after my last slide. So this is the takeaway message from the talk. So quantum computers are not a magic bullet to solve all hard problems, and nor are they by any means easy to build, as I hope you've kind of seen from some of the slides. However, I think that they do have very interesting applications, which are already being realized. And there's kind of a sort of more fundamental underlying point to building quantum computers, which is that if we want computers that really operate in the same way that the universe works, so we can understand and simulate the universe to our best predictions, then we really need computers that are actually operating using the same laws as the ones that we believe the universe to work on. So I think whether or not you think quantum computers will be able to solve, I don't know, all the world's problems, we should build them at least to do interesting physics experiments and learn more about the world. So that's the end of the talk. Thank you. Wow, I can't read everyone's comments. They're coming in so fast. Okay. Okay, so I'll just, what I'll do is, before I ask for general questions, I'll just answer Rob's question, which was to say a little bit more about the nitrogen vacancy quantum computing. And the idea of this is that, so it's kind of similar to the ion traps, if you think. You have small atoms which have basically energy levels, and if you can align them in a kind of regular array, and in the case of the ion traps, you put them in a line, and then you perturb one of them, and it talks to all its neighbors through mechanical and electrical interactions. So the nitrogen vacancy quantum computer works in a similar way, except you're doing it in a solid state environment. So you take a substrate, maybe three-dimensional substrate, for example, a piece of diamond, and you inject in it in a very regular array, sort of tiny defects. And I think this is why it's called nitrogen vacancy quantum computing, is because you put sort of small like nitrogen atoms in there. But you can do this with anything. It doesn't just have to be that. The idea is that you're introducing defects in a regular array into kind of a 3D solid. And then you actually have to have a way of addressing these tiny defects. So for example, one way you could do it would be using laser pulses. So you could address each of these tiny atoms using a laser pulse. It would change its energy state, and it would interact with its neighbors. And so the idea of this is it's really quite scalable, because you can imagine fitting millions of these qubits into a tiny, tiny piece of material. But in order to get the defects arranged in a regular array, you really do need nanoscale engineering to get them atomically perfect. So that's why I say that I think we need some help from nanotechnology there to do that. I'm not actually sure about the placement of the scale of the atoms, but I could find some links and some papers on that. It's not really my speciality area.
I'm not. I'm sorry. Hi,
You're
this
not.
is Natasha.
Well, you know, Natasha,
Okay, so
you're never shy.
I guess I should ask for
Randall,
any
how to
more
start,
questions.
I suppose you mean
Rob, I'll find you
You
some
go
links
into
actually
the
and send them to you, if that's okay.
tools.
Okay, so if anyone wants to ask me a question over the microphone too, sorry, I missed Julio's question. What is it? What was it, Julio?
Well, if you read the popular science, you read that many authors like to link somehow the very fact that quantum computing work to
Oh,
the
sorry.
main
Hang on a minute.
being perfect.
Oh, sorry. Could you just repeat that, Julio? Because my sound was being a bit odd.
Right. Okay. Some authors like to link the fact that quantum computing works with the validity of the many worlds interpretation of quantum mechanics. What do you think of that?
What do I think of that? Well, I think that quantum computing doesn't really provide any evidence for or against the many worlds theory, because I don't think at the moment there's any way to experimentally tell the difference between any of the different interpretations. So I don't think you can actually tell them apart using quantum computing.
This is also what I think, but some people think that the very fact that on a conceptual level, quantum computing can work and actually produce results. Perhaps not a demonstration, but a strong indication and suggestive evidence that reality can be similar to what Hugh Everett thought.
Yeah, I think that's a very good point. So one thing I would say about that is that the idea of quantum computing being perhaps it might be more powerful than standard computing suggests that there is some resource in quantum computing that is not available in classical computing. So some people interpret that as being the resource is being the multiverse or the many worlds interpretation, which I think is a good way of interpreting that evidence, and I think it's probably as good a theory as any. But I also think that we shouldn't forget that quantum mechanics is an incomplete theory. There may be something that we're missing. There may be a better theory that is just that would explain why we have all these different interpretations of quantum mechanics. So I think that while I'd kind of tentatively say that the many worlds seems like a good description of reality, I'm always open to there being something better coming along with when we have a better understanding of quantum mechanics itself. Because I think the fact that there are so many different interpretations means that we're kind of missing some clue or some piece of the puzzle, and I don't think that the answer will be any of those interpretations. I think it will be something much more profound and perhaps, in the light of new physics, much simpler to understand.
I would like to ask a question that's a bit more, I don't know, broad, I suppose. Quantum computing is a special purpose type of computing. It's something that you can use to solve a certain kind of problems, and you create an architecture to do that. Similarly, we could think of probabilistic computing, we can think of neuromorphic computing. We have a variety of different hardware ideas out there. Is there anything that we have not recently talked about that you think might be coming out of left field or somewhere that would give us another, something that would complement this whole field of new computing architectures that you would think of where you say, oh wow, we should pay attention to that?
Well, I think that people talk about all different kinds of computing that we can't even think of yet. So people talk about computing on very small length scales that's way outside of anything we're used to. So even things like quantum computing might be replaced by computing that works on different laws of physics at an even smaller level. So if you think things like physics at the Planck scale or physics at like quark computing or something like that. So there are theories that go even like string theory, for example. So if string theory was shown to yield any experimental results, we might be able to make string theory computers. Or I think anything where there's a law of physics that we're currently using as an approximation, there can be some sort of deeper digging going on there that might yield something even more interesting. So I think quantum computing is really just the first step. So I don't know if that answers the question or not. It's also a bit far out, but...
Yeah, it does. But it's interesting that you dig deeper down. You're saying go even lower, go to like quarks, go to subatomic particles, instead of saying something like, oh, maybe there's something at a higher level of complexity where there's also an interesting dynamic, like when you look at people using biology to do computation.
Well, I certainly...
that's just,
Yeah.
Anyway,
I certainly agree you can go both ways, and actually one of the things I'm really interested... One of the things I'm really interested in is this idea of massively distributed computing. So can you use tiny processing elements that are just in huge arrays? So like, for example, the smartphone network might be one example, but that's thinking really small. I mean, you could imagine things that cover the entire galaxy that are doing some form of computing that we really have no concept of or no understanding of. One thing that's interesting is even moving from the model of the logic gates to something like the adiabatic model is kind of a big step, and it's difficult to understand how that computing paradigm is different. So you can imagine there are things that are vastly more alien in the way that they're doing computation that we as of yet have really no understanding of. So for example, I mean, I think in some of the Greg Egan stories he touches on this, but
yeah, I'm thinking that there has to be a larger field around this, something like a mathematics of computation that can look at all the different ways in which you would like to be able to optimally solve certain problems, and then look for the computing architecture that would fit that from anywhere, anything you can come up with that works, and sort of like the bigger paradigm there.
Yeah. I think kind of some of the some complexity theory touches on this a little bit, but it's very difficult because once you get into the actual theoretics of this, you move away from actual building of things. So in the theory, people want to try and generalize as much as possible, whereas when you build something, you really have to specialize as much as possible. So I think there's kind of a bit of a dichotomy there. It's kind of, we want to understand as much about the universe as possible by condensing it into some very general principles. But if we actually want to then do computation, we actually have to choose one specific thing and make that happen. So yeah, I think it's like Randall was saying in the text, I think you need both, but that's why it's really hard to have an encompassing field that really looks at all these things. I think there's just so many possibilities. It's really, really difficult. Yeah. Okay, so are there any more questions?
If someone wants to ask more questions, perhaps the fastest thing is to just speak, because Suzanne may have problems in going back in the text chat. So I had the question, always related to many words interpretation. Now, it is my impression that quantum computing works by relying on information that would not be physically available according to any non-quantum model. Is this feeling correct?
Well, I think that you have to be careful when you're talking about information, because the actual information you can extract from a quantum system is always classical. So the computation may harness some quantum resources, but we can never see those directly.
Hello, Susanna.
Hi.
Hi, this is Tim. I
Hi
wanted to
there.
go back to something that you're already doing and working on, and that's back to the environment, adiabatic environment, which is something I
Yep.
work in, not related to quantum computing, of course. But I find that, and you touched on it earlier in your speech, that I know we have to run off the basis of classical physics and classical, I guess it's classical quantum mechanics, but in the environment it seems like there should be some simplified method in looking at how the natural aspects of how even our brain works, multi-level tiering and matrix and so on, neural networks, and I know I've seen in your blog some of the stuff that's been kind of worked on in that, but are you guys considering simplifying such an extreme environmental change to try and contain, obviously get the qubits and everything to work in a more simple, I mean, trying to keep it simplified, I guess you are, with such an extreme environment, but it seems to me that there's a more natural, if you will, I guess, more natural aspect to it that I think seems to be somewhat overlooked, because we have a tendency to make things a little more difficult, and then we always step back and go, oh, we could have done this a little more simplified. I mean, is there some point of observation that maybe you guys are looking at that you haven't talked about that says, well, maybe we can change our environment to get this adiabatic system in a different system without being so dramatic? Or, I mean, I'm looking at it from a practicality use. My gosh, to use that system is pretty heavy. That's just my thoughts anyway. Just curious if you guys are looking at some other type of environmental change to create the same effect.
Yeah, well, I think a lot of it does, from a practical perspective, a lot of it does come down to engineering challenges. So, for example, I worked on superconducting devices for a while, and I guess when I started in this field, and sort of a few years before that, the apparatus that was used for cooling was extremely inefficient. It was very bulky, and these things took up entire rooms. So the apparatus we work with is known as dilution refrigerator. But basically, over the years, even this technology has also been scaling down. So nowadays you can get what are known as cryocoolers, which basically sit on your desktop, and they will cool you down to 10 Kelvin or below. And they're really small and very efficient and compact. And the interesting thing about dilution fridge technology is that now there's a real application for dilution fridges, as opposed to them just being used for research. Now there's a real potential commercial application for them. You'll find that the companies and the people who make dilution refrigerators are suddenly very interested in, how can we improve the technology? How can we miniaturize things? How can we make this better? So it's not really just the qubit technology and everything that's being worked on. It's the whole system is also improving in a kind of Moore's law, if you like. So things like the cooling, the efficiency we can get from refrigerators is scaling, and the the way that we can reduce magnetic fields is also scaling. There are even potential technologies using microcoolers, which are basically on-chip cooling mechanisms, so you don't need to put your entire quantum system into a bath of liquid helium, which is what we really have to do in a research environment now. There are potential technologies which can really miniaturize this cooling, so it would just become like a commonplace thing in the same way that your desktop PC needs a power supply. Your quantum computer would need a micro cooling array or something, but what I'm trying to say is, like, the technology is also changing at the same time. It's not just sticking behind while we improve the qubits. So actually, I'm not sure if that answers the question or not, but
I have a more general question about D-Wave. Could you talk anything about QMC at home, and maybe what, like, I run it myself, and maybe what the work I'm doing is and how it helps the adiabatic process?
Yeah. So are you running the Aqua?
Yes.
One? Yeah. Okay, so what that's doing is, so if you remember, I talked about the adiabatic, the simulated annealing, and then the quantum annealing. So what Aqua basically does is it calculates the results that we would expect from doing quantum annealing. So this is a really interesting point because, so let me just say, for Aqua, for anyone who doesn't know, Aqua is a distributed quantum annealing simulation tool that is basically developed by D-Wave, and it uses the BOINC framework for distributed computing, which is the same one that SETI at Home and a lot of other popular applications run on. And the idea of this is that in order to calculate things like how your quantum energy levels are changing and how your qubits are interacting with another, you need to use this technique called quantum Monte Carlo. And this is basically a classical way of doing quantum calculations. So if you don't have a quantum computer, you can throw a classical computer at the problem to try and simulate what your quantum system's doing. And then you can compare that with the results from your real quantum system to see if it agrees. So what Aqua tries to do is it uses this quantum Monte Carlo to simulate the adiabatic algorithm as it's running, and then the results from running the real algorithm on the chips are compared with that classical simulation to see if the results are the same. So let me try and explain it. It doesn't you can approximate a quantum algorithm with a classical computer. It just takes a lot more resources. So to kind of make the point, I think Aqua was running for many thousands of hours, and it was using also thousands of nodes of computing power, and it was able to do some of the simulations that the quantum computer would be able to run in a few seconds or maybe a few minutes. So that's what Aqua does. It simulates the quantum chip so that D-Wave have something to compare their results with to see if it's in agreement with quantum mechanics. So you guys can all help by joining Aqua and donating spare CPU cycles to help simulate quantum computing.
I remember at one time you were asking to find out if there were any other methods in finding out and measuring the quark's performance. Is that correct? Have you guys developed any other methods other than what you're currently using, or are you experimenting with anything else?
You mean the qubits? Yeah. So
yes, qubits.
yeah. Okay, so there are various different ways. Again, it comes down to this idea of once you pick a specific model and a specific implementation, there's so much to explore even within that it's very difficult to change completely. So even to make superconducting qubits on a chip, you need an entire foundry just to make these chips. So it's very difficult to change from, say, superconducting qubits once you've decided to do that. But there are lots of things about them that you can change to see how it affects the performance. So, for example, you could change the physical size of the qubits. You could change how many other qubits they're connected to. You could change the temperature at which the system is operating at, and all these things are all parameters that you have access to when you're building the system. So it's not like we're short of things to try at the moment, and really no one knows how any of these things affect the performance. There's not even really a theory for it, so you kind of have to change things and just see how the performance improves. And I should say a little bit about the way that we measure performance, because I keep saying, well, the performance improves. So one way you can do this is by doing like direct quantum experiments on the qubits. So you want to make sure that by putting a qubit in this chip and surrounding it with loads of other qubits, that it's still behaving as a quantum mechanical object. So we do these kind of experiments on the chips. Then there are other performance metrics. So like when you start running what are known as problems on the chip, so these are like these traveling salesman type problems, you can then see how many times the chip returns the correct answer. So basically you run a problem that's small enough that you can solve it exactly using a classical computer. Then you compare how many times you get the right answer from the quantum computer. Then you change some parameter like the temperature or the size of the qubits, or I don't know, some magnetic fields on the chip, and you rerun all the problems and you see if the number of times it's returning the correct solution goes up or goes down. And that's really a performance metric for your system, because so when you run it on small problems, then you can say, oh, it's better or worse, because you know what the answer is, because you've used your classical computer to calculate the answer. But when you start scaling up to 100 or 200 or 1,000 variables, then your classical computer can't solve the problem any longer. So really, then you can run the thing on your quantum computer, but you have no way of checking it. So it's really interesting. So actually, knowing that quantum computer is working and is solving the problem is really hard, because by definition it's trying to solve a problem that can't be solved using a classical computer. So how do you verify it? And that's a difficult question.
Runs into a little bit of a paradox, doesn't it?
Yes.
Maybe you use your like you use another quantum computer, I guess. Just
well, we could do if we had one. Yeah.
Kind of a quick question. What do you think is the most interesting computation that's been done using a quantum computer so far?
Well, personally, I'm afraid I'm slightly biased in my opinion on this, but I think the training of the car detector, because it's actually something that was commercially useful. Like detecting cars in images is actually something that you would want to do, whereas factoring 15 maybe is something that, you know, is kind of cool, but it's not really commercially useful. So I would say that training classifiers like the car detector is the most impressive thing that's been done so far. And I can see that scaling quite well.
Can I ask a question? Another question? I hope they're not always too difficult.
Sure.
You talk about decoherence mostly as the enemy. Is decoherence always the enemy? Or is there a way that you have to or can use decoherence?
3 words, can of worms. Okay, decoherence is, well, I was saying that in the gate model, decoherence harms you, and that's kind of almost universally true. I can't really think of a way in which decoherence could help you in the gate model, but in AQC it's a bit more different. It's a bit different. So you actually there are different kinds of decoherence in adiabatic quantum computing, and one of these kind is related to temperature, and it actually helps you. So if you tried to do adiabatic quantum computing at 0 temperature, it wouldn't really work, because if you remember me saying the system has to find a ground state, well, in order to do that, it has to be able to change its energy, and the system can't change its energy unless it has an environment to interact with. Like, that energy has to get out or get in somehow. So if you try to isolate an adiabatic quantum computing system completely, it wouldn't really work. So unfortunately, it's extremely, the details of this are extremely involved, and even this is very difficult to calculate this even theoretically. So all we know is that temperature it actually plays a very important role in adiabatic quantum computing, and it's a lot more subtle than in the gate model, where you can usually say decoherence doesn't help you at all. It's bad, but it's not bad for all types of quantum computing, which is interesting.
Okay, thanks.
Okay.
Well, maybe we have time for one question. Does anyone wish to say something else?
I lost video feed, but Suzanne, sorry. It sounds like you guys are making some great progress, and I've been trying to keep up on it as much as I can with different means of information. So continued good luck with all that, and we'll keep seeing what's going on.
Well, thanks very much, and hopefully I'll be able to keep everyone up to date with developments and things. I try and put them on my blog if possible, so if people want to follow that to keep up with the work we're doing, and I try and report on advancements in the quantum computing field in general. So obviously just a plug for my blog there. It's called Physics and Cake, if anyone doesn't know.
Yes, enjoy your blog. We'll talk to you later. I'm signing off. Okay.
That's cool. Okay. Thanks very much.
That's really a beautiful dog. Show it us. It's a beautiful Labrador. What is it? A Labrador or a Golden Retriever?
It's an English Golden Retriever.
That's a beer thing. Okay, I'm going to switch the recording off now, both, and let's consider the formal of this presentation finished. Of course, I will be hanging around, and let's call it free time and virtual beer. I'm going to have one, in fact. Stopping recording now.
Just to let you know,
I'm thinking I might get some more coffee.
So I had one more question. Well, actually, I guess two questions. Actually, can you hear me? Okay.
Yeah, I can hear you.
Okay. At D-Wave, are you more of a like a hardware type person, or are you designing algorithms, or yeah.
Okay,
and also,
so
I
actually work in the sorry. Okay, I work in the hardware group, so I mainly work on the actually designing and testing the quantum processors themselves. There is some interaction with what's called the applications group as well. So they're the guys who are actually thinking about how we can use the processors to solve real world problems. So I'm kind of involved with that group, but it's not my my official position, which is testing the actual processors because doing so let me just say for Aqua, anyone who doesn't know, Aqua is a distributed quantum annealing simulation tool that is is basically developed by D-Wave, and it uses the Boink
playing the video.
for distributed computing, which is the same one that SETI at Home and a lot of other popular applications run on. And the idea of this is that in order to calculate things Carlo, and this is basically a classical way of doing quantum calculations. So if you don't have a quantum computer, you can throw a classical computer at the problem to try and simulate what your quantum system's doing.
Stop playing
and then
video.
you can compare that with the results from your real quantum system to see if it agrees.
Charlie, are you around?
So what Aqua tries to do is it uses this
stop
quantum
this.
Monte Carlo to simulate the
How do we figure out where it's
adiabatic
coming from?
algorithm as it's running, and then the
Moderator.
results from
Stop
running the
this
real
now.
algorithm on the chips are
but Julio
compared
went
with
away.
that classical
Oh,
simulation.
there he is.
No,
To see if the
Julio.
results are the same. So
Ah.
let me try and explain it. It doesn't.
It was hidden
you
behind the
can
wall.
Woohoo!
Were
Now
you
he's
still
stopped.
answering Michael's question?
Yeah, I think I answered. So I think I answered both parts. The second part being that there were about 50 people at D-Wave.
How do we get a copy of your presentation? Or is this available in Teleplace somewhere?
Yeah, I can put the slides up on one of the boards, or you can just grab them from the lectern. I think they're still on here. They should be in PDF format, so it's easy to download them.
I've recorded the entire session too. I'll try to post that.
Okay, thanks. Julia, will you be putting the recording, a link to the recording on your blog, or? Okay, I think Julia's disappeared.
I'm still here. I was just stopping something on the other PC. I'm back.
Okay. Oh, nice to see everyone's video feeds. I hadn't seen those before. That's cool.
Hey, Suzanne, one quick thought.
Hey.
What kind of books would you for people who want to know a little bit more about it? I know Seth Lloyd's got some out there, and Ford has another one that's pretty good. What others would you suggest? I don't even know if I got video feed or not, but what other books would you suggest others take a read?
I would think The Fabric of Reality by David Deutsch is a really good book, because it ties together quantum computing with a load of other useful and interesting, not just physics, but aspects of reality, I guess you'd say. There's some philosophical part to that. There's some stuff about computation and things like that. So I think that's a really good book. There's a book called A Shortcut Through Time by George Johnson. That is it's what I call kind of an overview or an introduction to quantum computing. So it's a bit like basically what a qubit is, and things like, if you want to know more about superposition and entanglement and things like experiments that were done to demonstrate them, then that's a good book to start with. If you're really interested in the maths and the theory, there's a great book called Quantum Information and Quantum Computation by Michael Nielsen and Isaac Chuang, but that's more like the kind of textbook Bible of quantum computation. So I probably wouldn't recommend that unless you're doing like doing an undergraduate course or like a PhD or something like that. The second book, sorry, was it's called A Shortcut Through Time by George Johnson. Yeah, I think that Preskel has a book. There's actually a lot of online resources, which are probably even better than the books. Yeah. So there's quite a lot of kind of quantum computing blogs and things like that too. It's a bit of a community. There's a web page called Quantiki, which is Quantiki, and that has a lot of links to a lot of the quantum resources on the internet from it. And you can probably need to stay away from. I couldn't possibly comment on that, I'm afraid.
Oh, really? Okay. I don't mind a bit of math. There was another web link that I saw in yours. I can't remember it, but a lot of the PDF files are on there. A lot of papers that have been published and stuff, which are really fun to read.
Yeah.
So I can't remember what the name of that site is. I think it's X. Gosh, I'm sorry, I can't remember.
Oh.
XI something. Every time I read a paper, it seems like it's always linked to that. So, I'm sorry, I can't remember.
Oh, Archive. Yeah.
Oh.
Archive. Yeah. Okay. I'll put that one in there.
Okay.
Oops. I think it's.
There it is. That's it. That's the one.
Yeah. Yeah.
Yeah. Thank you.
Yeah, that's the Archive is a preprint server. So basically, a lot of people in the quantum computing community will put their papers on there before they're published. So it's a really good way of reading stuff. The only thing that you have to be careful with Archive is that it's not peer reviewed. So you do get a lot of kind of like what I'd call crackpot papers appearing on there. So like every day there's something about someone that's that's solved some really important physics problem in their garage. But they can be quite fun to read too, actually. So.
Yeah, that's interesting. Well, good to know, actually.
Yeah.
Good to know.
Mm-hmm,
yeah.
Mm-hmm.
Resource is actually very important.
Mm-hmm. But yeah, the Archive is really good for, especially for quantum computing papers. There's a whole section of it, which is Quant PH. I think I'll just write it.
Yeah, thank you.
Which is dedicated to basically preprints of quantum mechanics papers. Of course, it's also, because quantum mechanics is spooky, then you do get a lot of interesting papers on that too.
You start getting the esoteric types coming in on that, or what?
Yeah, very much so. Yeah.
Ah, okay.
You get a lot of people trying to unite general relativity with quantum mechanics and other such things.
Yep. That seems to be a problem.
A lot of things about black holes as well. So, yeah. Actually, I should really put together a list of useful books and things to read and put it on my blog. So, kind of slowly over time, I've been building up this resources page, but that will probably continue to increase in magnitude over time.
Great, that's awesome. Thanks
it's
again.
Good to know that some people actually read it. Thanks.
Oh yeah, it's fun. It's fun stuff for me.
Mm-hmm.
Is there anything like a kind of a very short book, something like 80 or 100 pages, which gives the basic information, the really important stuff that one has to know without going into too much detail?
Yeah, well, I think that second one I mentioned, I'll just put it in here. It's it's kind of an introduction to quantum computing. So When I read it, I thought it was kind of a bit low level if you're in the field, but if you want a good introduction, it's quite good. So yeah, maybe I should write a book.
That would be a definitely good idea. The book you are talking about is this by George Johnson, isn't it? Or is it a short?
Yes, yeah.
Shortcut Through Time has been written by George Johnson.
Yes, that's right. Yeah.
I'm
trying to think of some others. I'm sure there are. I know a really good book. Sorry, I know a really good book. It's called The Quantum Brain by Jeffrey Satinover, and I didn't read it for years and years because I didn't like the sound of the title. But then when I actually did read it, it was really good. And it's not about what you might think it's about at all.
Who is that by?
Oh, it's by Jeffrey Satinover. And that's really good because he talks all about how it ties in with neural networks and like the Hopfield model. And he actually talks about adiabatic quantum computing, although he doesn't really call it that. But he talks about being able to solve problems by doing this energy minimization type technique, and how this is kind of what the brain does in certain ways. So that's also a really good book. It's a bit longer, but it's quite good. I'm trying to think of some more now.
I know there's a lot.
There are lots of introductory quantum mechanics ones as well. Like there's a Dummy's Guide to Quantum Mechanics or whatever that series is called. There's a load of Oh, there's one. If you're interested in the history of quantum mechanics, there's one that's called Quantum by I can't remember the name of that guy. He's quite well known. Oh my goodness, the name escapes me, but it's just called Quantum. That's kind of like, it's a historical overview of how quantum mechanics kind of the history of quantum mechanics, but it also talks about all the kind of experiments that were done and some of the principles like superposition, and that's also that's a very introductory book as well. So that's a good place to start.
If you're a visual learner,
I wish I could remember the name of the author.
If you've ever heard of the Teaching Company, they have a quantum mechanics course on there by Benjamin Schumacher. He's a good guy who did a lot of quantum information theory.
Oh, okay.
I would look into it. It's teach12.com.
Yes,
It's
someone remembered.
Check that out.
Okay, that sounds cool. I'll have a look at that. Yeah, it was by Manjit Kumar. That was it. I couldn't remember, but excellent. Thank you. Whoever the machine overlord is, thank you for gracing us with your infinite wisdom. There's also quite a lot of good online talks and things. I think Seth Lloyd has done a couple, David Deutsch has done a couple, and I think there might be some. It's either MIT or Stanford ones. There are some online lectures that you can watch, which are also really cool. And I put a couple of the talks that I've done on quantum computing in the past. I put them on my blog, so there's some in there as well. But yeah, so that's pretty cool.
What are some of the engineering problems that are very short at being solved? Is it just the decoherence and just having them talk to one another and exchange information? Is that the problem? What's going on?
So there are several problems. So that's one of them. That's kind of like an underlying fundamental problem that's always there. But there are a lot of other problems that you have to solve that are just engineering challenges. So, for example, when you try and make an integrated circuit with 20,000 components, then getting the process technique right is really difficult. So it's easy to make one qubit work or make a couple of qubits and get them to talk to each other. But when you actually start to try and fabricate thousands of, then they all have to work. So it's a kind of similar to the CMOS processes. So if you try and make hundreds of thousands of transistors on a chip, you have to ensure that every single transistor is working properly. And so you need like kind of very clean room environments and very tightly controlled processes to get that to work. But all that kind of stuff is possible. I mean, it's not fundamentally impossible, but it turns out to be almost practically impossible because of the way that quantum computing research is funded. So I believe this is a really big problem in quantum computing. The engineering and the technical challenges are not the problem, but it's having enough funding to be able to overcome them. So if you get enough smart people working on these challenges and you get enough funding into your foundry and into your actual fabrication of the machines, then you'll be able to overcome all the challenges. But it really is getting that amount of money to do a project like this. I mean, imagine if the semiconductor industry, how many billions of dollars it's had put into it over the years. That's just such a gigantic amount, and of course it's been augmented by all the kind of products that have entered the market along the way. So it's had a lot of feedback from consumers, and it's a huge industry that's sort of self-sufficient in a way. But quantum computing has nothing like that at the moment. You're trying to compete with this sort of multi-billion, maybe trillion-dollar industry. With something that's had at most few hundreds of millions of dollars put into it. And so to actually come up with a disruptive technology really does take a lot of money and time. And I'd say that you can actually also exchange money for time. So that's basically what it comes down to. I think all the engineering challenges can be solved. If the fundamental physics allows us to do it, then we'll do it. It's just a matter of money and time.
I think the reality of any of this ever coming to market is always going to be based on large business, big business bringing their money into it all. It's always a long process, and you're talking about something you're saying costs billions of dollars to do. It's just the reality of it. So you're working within margins that, like you say, you have parameters and you work within those parameters. So I'm hoping that that'll expand and give you more freedom, or this industry more freedom to grow faster. Just my thoughts.
Yep. I mean, I think it will. It's in the case of quantum computing, it's just a little bit tricky because it's not. It is a brand new technology, but you're really trying to do something that a current technology is doing, and you don't get any benefit until you've really scaled up to a large level. So, like I said, people still can run these problems on supercomputers, and they can get answers for them. And okay, they don't work for more than like 200 variables or something, but to get a chip, a quantum chip that could solve like up to that level is really hard. So you're actually competing with an industry that's already quite established. So you've got to do as good as that industry and then better, and that's really hard.
So that also raises the question: what about information? I mean, is there much in this that's actually protected? Or is it just pretty much open to public domain?
Do you mean like IP and things?
Yes, exactly.
So I'd say most of it is openly available. The only things that are really IP protected are the actual sort of very detailed sort of circuit level designs. I mean, they're the kind of thing that like ASIC designers wouldn't release their circuit layout diagrams into the to the general public. But really, that's kind of not the hard part. I mean, even if someone had access to all that information, they still wouldn't be able to make these things without a big foundry and stuff. Sure. So it's almost as though the IP stuff is really just a formality. I don't think there's anything that's if people start making quantum computing companies and they withhold information, I don't think there's much information you could withhold that would like slow progress. I think it's more about overcoming these engineering challenges, and everyone knows what they are. So
Right. So it's a race,
yeah,
basically.
yeah, it's a race.
To get it done. Yeah. Okay. All right. Well, like most things. Okay.
I'd really like to see more, actually more quantum computing commercial ventures. I think it would be really cool to have an entire industry built up around this technology. Yeah, I'd like to see that more. One of the problems, yeah. Again, one of the problems is that you can't get more than a few qubits without having a large-scale industrial process, and a lot of so what's been happening in research universities over the past 10 or 20 years or so is that there have been several foundries around the world that will make, well, at least in superconducting electronics, they'll make circuits for you and then you can test them. The problem with this is it's very difficult to control the process. So if say you measure your chip and you think, oh, it looks like these qubits are a bit too short, or there's some material defect in the process, then you have to go back to the foundry and kind of nicely ask them to change their process. And this whole turnaround, this kind of duty cycle of doing this it's not even months, it's years. It takes years for a process to be stabilized in a foundry, and the problem is that research grants don't run for that long. So what you find happening is that instead of academic institutions going, we want to investigate quantum computing, we're going to build the best chips we possibly can with like 100 qubits or something, you'll find that they're like, well, we could get 2 qubits from the foundry, which will work really well, and that we'll be able to investigate those for 3 years, which is the length of our grant. And so it's like if they asked for a 100 qubit chip, they'd get it, and then it wouldn't work, and they wouldn't be able to get it to work within the time frame of their grant. So I don't know if I'm explaining this very well, but this is why one of the reasons I don't think you can do this in an academic environment. I mean, you can investigate, you can investigate fundamental properties of the underlying qubits like one by one, but you can't build anything huge because you just don't have the time scale and the money to do that.
Well, I think that's why private business, in your case, is the best way to go. It's the only way you're going to maintain consistency in research and development. I hope for your sake and the company's sake it will continue.
Yeah. Well, I hope so too. And I think I'm very positive about it at the moment. There have been some really good results lately. And yeah.
Do you know anything about quantum mechanics affecting what they call wet technology, like how biology works, such as they thought that it would never affect biology, but maybe enzymes work a certain way because of quantum tunneling and things. I've read certain things. Do you know anything about that? Maybe I know it's not your expertise, but.
Well, no, I think it's very important, and as I mentioned, these kind of quantum chips have been used to start investigating protein folding, and it may be this is kind of a bit, it's mostly speculation, so this has not been proven yet, but some of the theories are that when proteins fold, they actually might use some tunneling effects to help them find a low energy configuration. And there are other systems in biology that also use especially tunneling effects. There are a couple I can think of off the top of my head. I think the olfactory system in some birds, like pigeons, is actually some of the detection of molecules that's done wouldn't work without quantum tunneling going on. There's also quantum effects in microtubules, which is the basis behind this orchestrated objective reality model that Roger Penrose and Stuart Hameroff have, which I am not a fan of. I don't agree with it. but you can't really dispute the fact that microtubules are of the correct scale, that there are quantum effects occurring in them. I just believe that that is actually then used to do any useful computation in the brain. But I think any biological system on that also scale up kind of proteins, maybe slightly larger, molecules, proteins, and a bit larger, there are going to be quantum effects there because these systems are of the right scale. They have the right energy scales. They're the right size to be dominated by quantum mechanical effects. So I definitely think they will occur in biology and also in nanotechnology. I think you'll also run into these problems. So one interesting thing is if we want to really understand biological systems and then nanotechnological systems, then we might want to start thinking in terms of quantum computation and how that could actually help us model some of these systems. So yeah, I think it's unavoidable. We should definitely embrace it rather than trying to avoid it.
I have a question. Do you think that robust quantum computing is required for uploading?
No. It depends how you define uploading, but I don't believe that you need quantum mechanics to make
whole brain emulation.
Machine intelligences. Whole brain emulation, again, it depends on the level of detail and what you're actually trying to emulate, but I think that you could emulate all the functionality of a brain without needing to resort to quantum mechanics to some level of function. I mean, it's kind of a weird argument because at some level, obviously, some of these effects do scale up. So it's like a bit like a chaos type argument. So you have a quantum effect on a very small scale, and does that propagate up to a larger scale to affect something in any way? So one question you could ask is, if we didn't have quantum mechanics, would we have brains? And I don't know the answer to that question because I don't even know the answer to if we didn't have quantum mechanics, would proteins fold correctly? So I would say that I don't know the answer to that question, but I suspect that you'll be able to replicate the functionality of a brain on a spiking neural net level or even a molecular ion channel level without needing to resort to quantum simulations.
Is quantum computing useful for whole brain emulation? I mean, will it enable whole brain emulation sooner? Yeah.
Mm-hmm. I think it will, but not through the mechanism of directly simulating parts of the brain. But I think if it turns out that, say, adiabatic quantum computing is exceptionally good at pattern recognition, then it might be that a better way to emulate a brain is to take some cognitive architecture that's like similar to a human cognitive architecture, and for the pattern recognition module, whatever that might be, you drop in your quantum coprocessor, and then you have an easier way of building a brain rather than just using a classical computer. So it comes down to this question of what computational hardware and model is the best to solve the problem you're trying to solve. So what I'd say about that is, if the problem you're trying to solve is we want to emulate an entire brain in silicon, then you have to start asking yourself, well, how do you design your silicon chips? Is general purpose computing the best way to do it? And it might not be. So I think what we can learn from trying to use different computing paradigms is that we can't just throw general purpose computing at every problem. Even problems like emulating parts of the brain might not work using general purpose computers. I mean, if you look at the computational power required to run the Blue Brain project at the moment, and that's simulating about 10,000 neurons, then there's obviously something highly inefficient going on there. And I think the inefficiency lies in the fact that you're trying to use general purpose computing to implement an algorithm that is just not suited for at all. So I think that quantum chips will be able to help us if the algorithms that the brain is running are very well suited to the same kind of algorithms that these quantum chips are good at running. So I don't know if that answers the question or not, but
no, that sort of makes sense. I mean, sort of like using I don't know, NVIDIA Tesla cards for doing graphics type, applications. You sort of want to use a specialized specialized computing for specialized tasks.
Yeah.
Yeah, why doesn't D-Wave get on the GPU computing? You would really get a lot more power then.
Well, I don't know. I mean, at the moment, the chips are designed to run a very special purpose algorithm, which is this optimization algorithm. So it might turn out that in the future, So the optimization algorithm is an interesting example because it can solve a lot of different problems, but it's because all those problems map to optimization. But really, the chip only solving one problem, which is this energy minimization, this traveling salesman type problem. So if you want the chips to run different algorithms, then you'll have to redesign them completely. So what D-Wave decided was that you're designing a special purpose chip to run one single algorithm. So you want to choose the algorithm that solves the most problems, and that's what the optimization algorithm does. So yes, I think that superconducting electronics and superconducting quantum computing in general could be put to a much wider use, but it's taken like over 10 years already to get this far. It's just such a humongous task. It's really difficult.
Suzanne, maybe you could give an example just for people's illustration of how having a special purpose hardware that solves optimization could change the way that we design algorithms in the future, whereas, for example, now we have to concern ourselves with the expense of doing an optimization algorithm as part of our program. But if we can have a special purpose processor like that, then there's a whole different way of going about iterative procedures. And anyway, maybe you can comment on that.
Okay, so were you asking for a specific example of that kind of thing?
If you have one. If you have anything in mind.
Okay, so one of the examples I could think of is something like detecting sequences in genes or something like that. Or matching, so pattern matching in gene sequences. So the way that you kind of do this classically is you just throw a lot of computing power at the problem. And it happens that for a lot of problems, your supercomputer or your huge distributed architecture is good at solving these problems. But when the data set gets much larger, it just becomes exponentially difficult to solve these problems. So even if you had access to a lot more computational power than we have nowadays, then you still wouldn't be able to solve some of these problems. And the issue I have with this is that these problems are actually here and now at the moment. So the amount of data we have from research that's being done in biology and in bioinformatics vastly outweighs the actual computational power we can throw at searching these huge databases of things like molecules, metabolomic pathways, and genomes. So I think that developing special purpose optimization tools to do what we're trying to do with this data, which is to do pattern matching and to do things like image analysis of spectra and stuff like that, is really useful. I mean, drug discovery is one potential application for this. So you're trying to find, you've got all these databases of metabolomic pathways, and there are certain molecules which interact with those pathways in certain ways. So if you can effectively say we add a certain molecule at this point in the pathway, and how does that affect the rest of the pathway? This is actually a problem that maps onto an optimization technique very well. So I think that could be a potentially good application for it.
Reverse phone book problem I brought up earlier kind of sounds like this. It was the idea that if you have just a phone number, how would you go through the phone book and find the matching name, because it's not in any sort of sequence? You would have to just randomly go through it.
Okay, yeah.
Right.
Yeah, I think that's probably a problem. That, do you know if it maps onto an underlying graph problem like SAT or something like that? Is it?
I don't know.
I can't remember.
I'm not exactly sure,
Okay.
but you know more about this, but you were saying that it wouldn't be able to run simultaneous problem solving like that, and that's kind of what the idea was, is that you could run all the possible phone numbers and then pull out the name in a lot fewer steps than just running linearly.
Okay. Yeah. I think this is so before I was mentioning an algorithm called Grover's search, and I think that sounds very similar to what you're describing. So Grover's search is an algorithm for searching an unstructured database. So normally what you have to do if you're doing this classically is you're using a brute force way of searching, because there's no information, there's no structure in your database for you to be able to find like which phone number corresponds to which name. So you'd have to go through the names one by one and check the phone numbers against them. And so on average, you'd have to check half the entries in your database before you found the right one. However, with Grover's algorithm, the idea is that you only have to check root n of the number of entries. So it's actually, for very, very large databases, you get quite a much more efficient algorithm way of searching. So I think that might be the problem that you're thinking about. And Grover's algorithm is, again, it's one of the ones that can be mapped onto the gate model quite well. I think it can also be mapped onto AQC, but I don't know how to kind of go about that, if you see what I mean. So a lot of these algorithms can be mapped onto, like, from gate model to AQC or vice versa, but there's some overhead in it which may or may not make it more efficient. So
what is the first really commercial application that is coming to the market? I mean, the first thing that really requires quantum computing to be solved efficiently, which is kind of an important commercial application with a market value, and that could be achieved in a reasonable number of years with a reasonable funding.
Okay, well, I would say, in answer to that, I would say something like the machine learning applications, because they are applications that people have had such a hard time with over the past several decades, that I can see there being a niche there for these quantum computing architectures. And the reason is actually quite subtle, which is these are not problems that are by definition difficult classically. I mean, our brain manages to do it, so it can't be that difficult classically. But the problem is we've never designed a computer architecture that actually looks anything like the human brain. And I think that these quantum processors are actually they're closer to that kind of style of architecture than the way we classically build processors. So I think in a way, the applications are not so much coming from the quantum nature of the processing, but just from the fact that you're building an entirely new type of architecture, which is in the way that the thing is interconnected and the algorithm it's running is very different and very new. So whether or not it's using quantum effects in the way it works is, I think, almost secondary to the point that you're building something that's just totally different than to anything that's been built before in terms of architecture. So I think we'll start to see these kind of chips being used for things like the machine learning applications and image recognition, feature detection, and things like that. I think that will be one of the main commercial drives. So you might just say, well, why can't people just build, classical processors to do the same thing? Maybe they'd just be just as good. But I don't really know of any classical algorithms that work in the same way as quantum annealing. Like there's simulated annealing, but I'm not sure it's very efficient.
Suzanne, you talked earlier about the fabrication methods and the sources of materials. How do you see this worldwide? How do you see, from where you sit, what's your viewpoint of who's kind of leading the industry race now, the governmental race to build fabrication devices and try to keep up with the demand for research in this area?
Yeah, so there's several fabrication facilities around the world that can make this kind of electronics, but I think that the best ones are in North America at the moment. So I think that the problem is it costs so much money to set one of these things up that I think eventually there'll be maybe one or two around the world that do it really well. So there's a couple in North America, there's one in Japan, and there's one in Europe that build this superconducting hardware. But I think because it's so hard to do, and anyone who gets a slight competitive edge will get all the customers straight away, that I think it will end up being a minimal number of foundries with lots of customers. And the other driving force towards that is that foundries work better the more customers they have, because the more they're running the process, the more wafers they can get through their process, the better the wafers are, because they've got a lot more data to see if the process is tightly controlled or not. So I think that you'll find that there'll probably be, in a few years' time, there'll probably be one or two really big foundries, perhaps one in the States, one in Japan, something like that, doing this kind of work.
That's very interesting, your comments. When I was at NASA 10 years ago, before I retired, we weren't leading the field in that area. And the theory was that other countries were going to pick up the fabrication faster. So really glad to hear your response. Thanks a bunch, and thanks for a terrific presentation today.
Okay, thank you. That's great. Thanks for listening.
Sorry for that, someone must have switched the recording.
Great presentation, Suzanne. I'm logging off. See ya.
Okay, thanks very much for coming.
Okay, bye-bye.
Bye.
Thanks again, Suzanne. It was absolutely terrific. I really appreciate it. I know everybody else did too. All the best to you.
Okay, thank you very much for coming.
Are there going to be any other lectures hosted, Julio, in the future, in the near future at least?
There is next week a lecture by Ben Gersel about things significantly less technological and more philosophical than today's lecture. And I think these two things make a nice complement to each other. Ben Gertz will be talking next Sunday on his recent book, Cosmist Manifest, which I can very much recommend everyone because it's a great book. And I think immediately after Ben, we'll go back to things more having to do with technology. But I think every now and then it's good having a break to see things in a big picture, and from what I like to call a cosmic perspective. Everyone is welcome also to next week seminar, and I hope to see everyone.
Also, I recorded the entire session. What would be the best way of giving it to you, Julia?
Well, if you have finished recording, you will see a little icon floating close to the head of your character. What you do is you just drop it on a screen. If you can stand up so I can recognize you. I know that you have a green avatar.
I'm right behind you if you turn around.
Right. So let's go close to a screen. For example,
I'm going to stop right now. It's at hours 33 minutes.
Right. So